Good morning. Or good
Good morning,
afternoon.
Pete.
I should say good afternoon. You're still in Amsterdam, right?
Yeah, well, yeah.
You live there, so
I live here, and it was great seeing you last week at the Things conference.
Yeah, no, that was great. I hadn't been to Amsterdam in a few years, and yeah, it's such a nice city. And
Did you get into the center though? Because where we were at for the conference was not really Amsterdam.
yeah, no, I had a little extra time. I went to the Rika Museum
Yeah.
and
Oh, awesome.
things, and yeah, and that was a great event. So hats off to Nikki Geisman and team over there at the Things.
Yeah.
Things people. And yeah, it was great. It was the first time we had brought a bunch of the Edge AI community there, and I know Edge Impulse has been a long-time supporter as well. But
and the scavenger hunt was awesome. I thought it was such a great idea because this was actually the year they had like double the partners, double the booths. It was huge this year. It was really fun. So I can't even imagine what they're going to do next year.
I know. No, it was good. And we had I was on 4 panels myself. There's a bunch of Edge AI panels and talks. And
you're a busy man, Pete.
It was a busy week. But yeah, it's, I was telling people the intersection of low power wireless and low power AI is kind of a good overlap. So I think cross pollination there. So that was fun.
For sure.
I'm de-jet lagged, and apologize to some of the folks that joined earlier. We had a little scheduling.
Yeah, I saw the comments. There was people here like.
I think we had originally accidentally scheduled it for 7 a.m. Which we always have it Tuesdays at 8 a.m. And so with that, but it's a lot.
Always blame it on like daylight savings time,
Yeah, that's it. Okay, cool. So we're here, and we're going to bring on Evan, and we'll talk about his topics. And they recently rebranded, so some people may have known them as Eta Compute, but now they're called Model Cat, which I think.
Yes, I was just going to say I think that's a much cooler name. Their logo is also cooler, but it's so different. I was like, wait, who is this?
Everybody likes that.
But it's so exciting to have the CEO on today, Evan.
Yes. Oh, let me do a quick PSA before we bring Evan on. So if folks have not, or if you're in the area of Taiwan in November, or interested in going, we're going to have a 2-day event in Taipei, November 11th and 12th, and Edge AI Taipei 2025.
I might be there.
Cool. Yeah, here, I'll show the little banner. If you go to that URL, there's still some seats available. It's a bit of a limited seating thing, but we're going to have, Jenny might be there, Edge Impulse, but we're going to have, your parent company, Qualcomm, I think will be there too. NXP, ST Micro, Dell Technologies, Advantech, Intel, Climax, and then we're going to have professors from NTU and NTCU, and a bunch of cool presentations on research. And we're going to have a cool mixer there. We're going to have a panel on startups, a panel on deploying and commercializing Edge AI. So really kind of a packed couple of days to meet who's who in the space and learn what's what. So go to that URL, you can get some tickets, and I'll see you there. So that'll be good. So that's my PSA. Now that we've done the PSA.
Well, another quick PSA. If you have any questions today, please ask them in the chat, and we will answer them live at the end of Evan's presentation. So
yes, and we may even interrupt them depending on
how juicy the question is.
Sometimes it's good, you kind of bundled in there. But yeah, definitely, this is interactive, and this is your opportunity to talk to the experts on what they're talking about. So yes, please do that. Why don't we bring Evan on board here? There he is.
Good morning.
Morning.
Good morning, Evan. Yes, excellent. So yeah, thanks for joining us. Let me get you into the guest configuration here. So let's see. What happened to you? Did I lose you? I lost you for a second. There it is. No, but I want to give you a guest spot. There you go.
Here I am.
Yeah, you got the primetime spot.
Thanks.
So the banner so that your name comes up. So you're the CEO of Model Cat.
Yep.
And welcome.
As you said, people may have known us as Eta Compute, but we recently rebranded as Model Cat. Wanted to really reflect our new mission, which we'll be hearing about a bit today.
Okay. What was is there a backstory to model cat? Are you a cat person, or what's this?
Yeah, well, like all of these things, we're back annotating the myth in real time. So I am a cat person, and I do, I do have a cat, and in fact, we've got quite a few cats in our company.
Okay.
But it was more a thematic thing, the way cats always land on their feet and have this kind of poise, do stuff that seems difficult, but with, out getting their whiskers out of joint. So we had this idea of using the cat for that reason.
Got it. And you're based in Sunnyvale, I think you said?
Yeah, in Sunnyvale in California, Silicon Valley. Yeah.
The heart of Silicon Valley. So that's exciting.
That's right.
Good. Well, appreciate you joining us today and enlightening the audience. As Jenny said, throw some questions in the chat. We may chime in on occasion if we get a good bundle of questions. But then I think you have a presentation you were going to go through, and you have a live demo too, right? So
yeah, I've got a prezzo and a demo. Yeah,
we like live demos here because that's let's see it working.
Yeah.
Okay, let's bring that up. Yeah, cool. So I think Jenny and I will kind of hang back a little bit.
Okay.
Give you the floor, as they say, and then, like I said, keep those questions coming. There was a question I'll answer right now. So someone asked, was Edge AI formerly TinyML Foundation? Yes, we used to be called the TinyML Foundation. Speaking of rebranding, in fact, I was sharing with Evan before that we got started how it's been about a year where we changed the name from Edge AI Foundation to from TinyML to Edge AI. So, yes.
Weren't you the mastermind of that decision too?
Yes, I guess I was. Yeah.
I think it was a good choice because it really does expand what we can talk about and do.
Yeah, and then we have been. Yeah, there's all kinds of generative Edge AI things happening, and computer vision, and all kinds of goodies. And so rebranding is important. So I appreciate that Evan and the team have made the leap. But yes, we did our own rebranding last year. So we still say from TinyML to the Edge of AI. We love TinyML. It's a critical part of this whole process.
It's a component of it. Yeah.
So, but yeah, okay, cool. So I'll just do that. Okay, so we'll step back a little bit. Evan will give you the floor and take it away.
Great. Well, thanks for having me this morning, and welcome to everyone watching. Appreciate your time. I'm Evan Petritis, and I'm the CEO of ModelCat. And as you just heard, we formerly were called Eta Compute. If you've been in this game for a while, you may have heard of Eta Compute because we were originally one of the edge inference silicon companies. But we pivoted away from that, and we have a new mission. And the name ModelCat comes along with the new mission, actually. And now, really, our goal now is to build tooling that gives you truly autonomous AI model production. And that is actually a pure software sort of proposition. But we actually have a bunch of hardware components that you'll see a little bit of as we go through today that are part of our ModelCat solution. And you will see echoes of the origin story in that probably. So I wanted to spend a few slides and then we'll get to the demo. And I'll leave plenty of time for some questions at the end. And I guess they're going to interrupt me if they get a really good one. But a few slides first to sort of explain our philosophy and what we're trying to do here. Starting from what we see as one of the key observations, which is the velocity of change in the AI domain. So, I've kind of been in the technology industry for a long time and seen, I was very lucky to be part of the internet boom, see the internet grow from, an academic network up to, what it is today. And that was a lot of change, but it never had the velocity that AI technology, velocity of change that AI technology has seen. And, it's really like we're seeing a new innovation every day. And the problem that development teams basically have is they see, you might read an abstract for a paper, or you might read a press release or a data sheet from a chip vendor. And then if you're trying to actually develop products, that very often the question in your mind is this innovation important enough for me to pay attention to? Will this give me some kind of meaningful business outcome that I need? And, examples of these things, every day there's more neural network architectures. The chip guys have been extremely busy with different hardware architectures. We're in the early, we're in the phase where the hardware architectures are still proliferating, actually, even today. It could be something like, a new approach for training optimizer, or training scheduling. So there's basically a fire hose of research and new ideas in the field. The issue is that these are or some of these at least are probably applicable immediately, but it's very hard to know whether you should invest your time in investigating, even reading the whole paper. Should I read the whole paper? It's a question that is actually a hard question for any of us to answer. So this is like a characteristic of a technology that has got super high velocity and kind of unlike anything that we've seen in the past. And the background environment to this is, if you're trying to build products, there's a pretty well established toolkit for how you do good product development. You have good system architecture, you do decomposition. This is all engineering come software engineering kind of motherhood and apple pie. You build in testability, you stand on the shoulders of the giants, you use platforms and mega components, those platforms that we use all the time. You maybe don't even think about the operating systems or the IP protocol stack, the whole internet stack. You do a lot really of incremental improvement. So trying to reuse, because it's so hard to get stuff to work in the real world, that once you've got it to work, you don't want to lose that. So there is a lot of building on modules, on components and so on that you've already proven out or that have been shown to work. So this is all great. But you spray a fire hose of AI innovation at this, and none of these kind of mechanisms and none of the processes in traditional product development are really capable of responding and absorbing those innovations fast enough. It's really a pretty tough situation if you're in the game of trying to build real products. So we wanted to address this. And so, of course, we aren't the first people to observe that this is a problem, this mismatch. And people have tried many approaches. And some of the approaches, there's actually, a couple of other major ones as well. But some of the approaches are, better libraries, maybe if I make my compiler better, or maybe if I make my, my training setup better, or my cluster management better. This component by component improvement, it's part of the story, but it's not really been enough. Another sort of angle is the whole product angle, which is, okay, the issue here is that we just need an end-to-end tool chain, which gives a development team everything they need. And that gets part of the way as well, but has not been dramatically successful. And of course, the one that many players in the game come back to, because it's actually kind of known to work, is here's a CAN solution. Okay, here's a CAN solution for X, for problem X. This is known to work, and it works, but it gives you these spot points in the product space where you've got a solution. Then to get from that solution to actually something that is useful for your application is not always easy. So none of these have really been broadly successful. And we set out to ask, how can we actually solve that problem today? I really like this stock image, or don't like it, in the sense that, they put it at the word AI on a chip. It must be easy, hey? That's it. There's the picture. So that's, in some way, that's what we want, but it's been proven to be not very easy. But we have one hugely powerful weapon that we have never had in the past to help to solve this problem, and that is AI itself. Using AI as the core of the tooling for this to help solve this. How do I build AI models for a particular application on a particular chip? That is the key to making this a broadly accessible and usable solution across a variety of different domains. And that's what I'm going to show you today. That's what ModelCat is. So, as usual, AI is really critical and is the linchpin of this, but it's not a magic wand. And anyone who, uses any of the coding tools or even any of the chat AIs today knows that you need some scaffolding. You can't just throw a general purpose AI at a problem where you actually want a very deterministic and well characterized output, which is really what we want if we're trying to build a product. And so AI itself, it's not really a magic wand, but it's the central component. And we've built this scaffolding and kind of characterized it as 5 pillars that you need for AI-created AI. So the very first, and probably I think the most important one, and look, a lot of the chat bots are now getting to this, is that you must have a closed loop around the AI. That is, the AI is working towards the user's goal in a closed loop until it reaches theirs. And so, of course, then that brings up, how do you limit how much resource it's going to use and all of those sort of things? Yeah, you have to think about that. But this is really the central architectural characteristic. The second thing is it must be grounded in reality. We're not in the game of dealing with AI hallucinations or inaccuracies or estimates. We need the AI to be continuously grounded in reality. And, I use that term very broadly. The reality of what the chip can do, the reality of how much memory you've got, the reality of how much power it's using. It must be grounded in reality. And I'll tell you a bit about how we do all these things in a minute. Third thing is, it's got to think in systems. I've got a sort of system. So I'm actually a hardware engineer originally, and I've got a systems background. And the thing that we need to do here to make this broadly applicable is provide a way that you can tell the tool or the platform, ModelCat in this case, you can tell it in a natural way what you want out of it. So this is not the same as giving it lots of little micro instructions about what neural network architecture you want to use, or exactly which transfer learning data set you want to use. It's, here's what I need from you. And, it's an input. Now you give it to me. The fourth thing is all about that fire hose. We need a way, the system is modular enough that it can learn from this fire hose of new research, and that can be highly systematized and highly automated, that learning. And then the last one is that it needs to be a trustworthy single-step process. And, trustworthy in the sense that the user really trusts it. And of course, that's something that builds up over time with using any of these kinds of AI systems. Okay, so now let me just skip over to very quick kind of demo walkthrough. So ModelCat itself is a SaaS or cloud-based system. And so I'm running this is in my browser. I'm running this in my browser, and you can see here the datasets page. This is showing a variety of different datasets. And today I'm just going to concentrate, show you one particular dataset. So this is a dataset that's a public and open source dataset that's been bopping around. It's pill detection. And so, you can probably see that they've got a variety of, somewhat difficult backgrounds and distractions for the system to try to find pills within these images. And it's a good example, just simply because it's easy to understand. So within ModelCat, of course, there's a way that you can upload your data, and this data set has been uploaded by one of our engineers, actually. The system provides a bunch of analytics on your data that helps you to quickly understand if you've got the typical sort of data skews, and our AI will sometimes give you a warning that says that, like in this case, it's saying that it's found some distributional shift between the training and validation splits. So there's the system automatically analyzes your data set, and then will give you warnings, and sometimes even up to the error level if there's things that are wrong with your data set. This is all a pretty simple press button process to get that data in. Now, one other kind of core input into our model creation, or as we call it, the model build process, is our silicon library. So we have a variety of chips that have been onboarded onto ModelCat. When I say onboarded, that means that ModelCat has characterized each of these chips for their ability to run these neural network models. And it knows just about everything that you could need to know about the kinds of operations that are supported, how fast they are, how much memory they take, what the parameters that they accept are. So you can think of this as a very detailed, highly automated profiling of the chip and its low-level runtime. Most often there's a runtime that the chip vendor makes, and sometimes, in some cases there's specific kernels that chip provider provides, and in other cases there's actually compilation code or compilation tools that the chip provider provides. So all of that is characterized by ModelCat. So you can think of this as the library of chips that you can target for your model inference. And then when it comes to actually asking ModelCat to build models for you, it's a very simple process. So you basically can specify the data set here. So I might take this pills data set that we were looking at. So I've just selected the data set, which is one of those data sets that we looked at earlier. The system, you might have noticed then that it auto-populated a bunch of stuff. So this is the internal AI at work. It knows something about that pills data set because of all the analytics, and it makes a bunch of decisions about the best way to set up to build a model for that. But the one thing that I still haven't told it, which is critical, is which chip do I want to target? So here I have, again, that same library of chips. So maybe I choose this NXP IMX8M Plus chip. And once I choose that chip, this left-hand pane is really everything I need to tell the system. That's the essentials of what I need to tell the system. I want that model, I want models built to solve this pills data set on this chip. If I like, I can optionally specify, I would like, I'd like the inference time to be less than 5 milliseconds. Or perhaps I've got a battery powered device, and so I'm very worried about energy use or power. So then I can specify the energy per inference. So these are constraints that you can give the system which are optional. And you can see here that there's a little AI advisor pane down at the bottom here. So I don't know if you can see it on your, if it's big enough, but it's saying that the job success prediction for this is high, which means that with this set of constraints, that data set on this particular chip, and with the constraint of, say, a 5 millisecond inference time, it's expecting that it's a high chance of getting success on that data set. Before we leave this page, I just want to show you the advanced option. So that when I click the advanced option button, there's a huge number of panes that pop up, and you can get inside and start giving the thing much more detailed directions. So you can specify the input color space. If you think you know better than what the AI knows, then you can specify resolutions for the inputs. You can specify target values for accuracy, how much memory you want to give it, any of these parameters, and then a whole bunch of stuff about how it does the training and optimization. Let's turn that off. Now, I wanted to, so when you hit this create button, the system goes off and it does a lot of things. And I'm just going to skip back to a slide for a moment, just to tell you the things it's doing. So behind that button, the system is taking its understanding of your data set and its understanding of everything it knows about the chip that you specified as a target. And it's starting to ask itself questions. It's starting to ask itself questions about what would a good model architecture be for this? So this is neural architecture search. What would a good transfer learning data set be for this if I have one? And then it does some testing of those hypotheses. And this is really important for that grounding thing that I mentioned. The system has access to what we call the chip farm, which is literally a hardware array of all of the chips that we've onboarded. So in that case, I was using the NXP IMX8M Plus. So within our chip farm, we have a bunch of those chips, the real hardware. We have the NXP conversion tools, the latest version of the NXP kernels. So the system is able, if it needs to go and test its hypothesis for, I think this model would be a good candidate, good model architecture for this problem. It's able to go and test that on the real hardware if it hasn't tested it before. And what it gets back from that are things like what's the accuracy, what's the inference time, and what's the energy per inference. So all of that is rooted in real measured data. And then the system can, once it has some neural network architectures that it thinks are very, likely to be successful and come in under the constraints, then it starts to expend more computation on training and hyperparameter optimization of those neural network architectures. And it's continuously learning. So every time it sort of tries out a new architecture on a particular chip, it learns all of that, and it essentially has a big knowledge store inside it. Okay, so now if we go back to, so I've created the job, and then I come back sometime later. So during this time, the system has done all of those steps, spun up a cluster of computation for training and other computation intensive stuff that it's doing, and then it starts to give you results. And this is a pretty typical example of a results page. So it says here that it's actually the pill detection data set, and we kind of collapsed all of the complexity of the data science results down into a single page, which starts off with, here's a graph of my prediction time versus my accuracy. So x-axis is the prediction time, or the inference time. Y-axis is the accuracy, and that particular metric that it's chosen there is whichever the original job chose as the primary metric. So, you might have seen scatter plots like this before. Every dot on here is a model, and up and to the left is better. The black line is the Pareto frontier. So the most interesting ones are generally on the Pareto frontier. So if I click on one of these models, then I get, a whole bunch of detailed parameters, all the different metrics there if I'm interested in different metrics. And you can see that the system understands and reports measured accuracy metrics or data science type metrics, as well as these kinds of things: energy per inference, prediction time. These are very, very hardware specific things, or RAM usage, ROM usage. And so you get a complete picture here of the performance of that particular model. You may be satisfied, and at that point you can download that model. And if you download and run that model on that same chip, remember this is all, actually this particular run was targeting an ST chip. If you download and run that on that chip, you'll get the exact same performance. So this is guaranteed because this is measured. These are measured performances. So this is avoiding the problem that you often get where, the tools need to do an estimate, or you're doing your data science in a more abstracted environment, building the models and measuring them in an abstract environment. And then you've got this porting or deployment process to get it to work on the actual chip. In this case, the numbers are measured on that chip. Okay. And then, within each of these models, there's actually gruesomely detailed reporting. And this is all normalized. So it kind of makes it nice for the end user, because it's all normalized from the vendor's ways of describing this stuff. So the low level, the different SDKs describe this stuff or report this stuff in different ways. We normalize all of that and basically provide very detailed reports which are very comparable, one chip to another. And so this is actually called our model benchmarking report, which is, as you can see, is mainly around layer timing and sort of resource usage on chip. And then we also have this model scoring report, which is all the data science metrics in gruesome detail. So just going back to here, I just wanted to show one more thing. Within this graph, you actually can access all of those different metrics. So if you decide that, oh, you know, Cocoa MAP at 0.5 isn't what I'm interested in, I want it at 0.75, it's just a simple matter of, you know, selecting that off this axis. So, you know, a lot of the sort of stuff that you might otherwise be doing in, you know, writing a lot of Python code, that the sort of day-to-day stuff is done by ModelCat in a very easy way, an accessible way. Okay, so with that, I'm just going to skip back. I'm going to finish up now so that we have time for questions. One more thing I just wanted to mention. ModelCat has a partnership with NXP, and we co-developed a version of ModelCat with them called EIQ Model Creator, which is their cloud-based ML enablement platform for all of their chips, all the way from MCXA, which is a relatively inexpensive, low-powered microcontroller with no acceleration, up through the RT series and the IMX series, multiple series of IMX. And so we've got ModelCat, which is our own brand and our own product, and then we've got the EIQ Model Creator, which is co-developed with NXP. All right, and I invite you all to do a test drive. Give us a yell, and we'd be happy to give test drive licenses. Okay, that's it from me. I'll leave that up there for now. Questions?
Cool. Well, thank you, Evan, for running through all that. That was pretty cool. And we have quite a few in the queued up here in the chat. I know, Jenny, do you want to do the honors? You had some good questions on your own too. So
I got some questions in the chat. However, we just got one from Dimitri in the comments, so maybe we'll do that one first.
Throw it up there.
So Dimitri asked, can you export your models to PyTorch or Keras, or is it only to the hardware that's supported by ModelCat?
It is. We do have. We're kind of more in the Keras universe, so we have a direct export that will get you into Keras, but not PyTorch today.
Okay, that's good.
You know, the standard output, the chip guys have made it relatively simple for us. On the chip side, TF Lite, you know, is still the dominant interchange format, and we support that. So for almost all the direct to chip interactions, we output TF Lite.
Okay.
Sounds good. What are some of the other questions we got here? Jenny, you had some good ones.
Yeah, I just asked some questions sort of chronologically throughout your whole presentation. I guess the first one I had was I know you showed an image classification, maybe even bounding box, object detection example, but what are the other types of models that you can generate with ModelCat? Is it just computer vision, or can you do time-based frequency?
Yeah, we've done, okay, so it's mainly computer vision, the usual computer vision use cases. We have done a bunch of single dimensional, time series data type stuff, and people use it for that and have used it for that. And we are also working on other modes. So, you know, obviously the language models and so on are coming probably not going to reach these little microcontrollers, but we already have chips that are large enough to run language models, for example.
Mm-hmm. Cool.
Here's one that came in from Dale. Will you be supporting more MCUs?
Yes, we keep adding various types of, some of them are MCUs, some of them are really microprocessors, some of them are these special purpose inference chips. We keep adding more, and the nice thing about it is that we've now got a kind of factory for adding those. This is not a highly artisanal process to add to onboard those chips. So yeah, we are, and we work with. You can see that we work with the major vendors to date, but we've got some very interesting discussions going on with a bunch of the startups at the moment, which will sort of supplement.
Is there like kind of an SDK or a hardware development kit? If I have my own chip, I could kind of create some libraries to plug into your stuff.
Yeah. Down the road. Yes, so we've got a roadmap bullet point for self onboarding, and we are working towards it. It's not there yet. So right now, it's still a bit of engineering work that one of our engineers has to do. So
I guess my follow-up question for that would be, do the embedded engineers use AI to generate the support for a new platform for the AI generating AI? You know what I'm saying?
Yeah, no, I know what you're saying. No. I think, the deep embedded stuff, and of course the last bit that the embedded engineers on our side are doing is the deep embedded stuff, right? You can imagine.
Yeah.
We've got some great ideas about how to do that. Today we haven't done it.
Awesome. Well, we got a couple more questions in the chat as well.
Yeah. Should we do the Qualcomm one next? Why not? Of course, the KCF 490.
Yeah, so we've got not that Qualcomm chip. We've got another Qualcomm chip whose name I've immediately forgotten on there at the moment. We're pretty happy to work with whichever vendors, and we tend to be driven by, the business opportunities.
Sure.
In terms of sequencing the chips on. I believe that 6490 uses the same
MPU.
It doesn't really matter to us, but as long as the SDK is the same, and I think it does use the same SDK, and they've changed the name of their SDK a couple of times.
Right. Part of the DragonWing world there.
Yeah.
Cool. Actually, I got a quick question. So we talked about architecture types and things like that. I mean, one of the panels we had in Amsterdam was what we call the farthest edge, talking about spiky neural networks and neuromorphics and things like that. Have you done any experiments with that in terms of portability supporting kind of more spiky neural network type of?
Yeah. So we're talking to a few of the startups in that and a couple of those do these kind of spiking neural network type approaches. I mean, the general architecture that we have is very, very applicable to that, but the lower level, doing jumping the abstraction gap between where they are with their runtime or whatever, the chip vendor's runtime and where we are, which is, we speak pretty standard neural network architectures and interchange formats. That's a bigger step. Now that said, I'm hoping that in the next 6 months or so we have one or other of those that gets mature enough that we get it up into production.
Cool. Here's a question from Dmitry Godovsky. Do you have KWS or WWD models? Maybe you can enlighten the audience as to what those acronyms mean.
AW.
I don't know what those mean.
KWS is keyword spotting.
Yeah. We've audio keywords we've done. Yeah. WWD.
WWD I need to look up.
Yeah. Okay, that's not one that I'm familiar with. I'm sorry.
All right, Dimitri, if you can enlighten us in the chat, what is WWD? What else we have here? There's a question from Katya. Latest research papers at the beginning as well as NAS.
Wake word detection. Sorry.
Wake word detection. Oh,
okay.
Yeah.
Oh, yeah. Okay. Yeah.
Okay, model building AI closer to NAS, or indeed managing to learn from the latest research? Yes.
Yeah. So our general approach is a superset of both of those. So this is really important, actually. You think about how a human learns. If you're someone who's working in research in that field, how do you learn about new ways of doing things? I use that, and it sounds like a very, very high level description, but you have to jump up to that level to get this point. You might read a paper, or you might scribble on the back of a bit of paper and go, oh, if I take a mobile net 3 and replace this block with something else, then I've just done some neural architecture research, or at least ideation, and I've got a new neural network architecture. So it's both is really the answer to the question that's asked here.
Good.
Oh, I had a quick question. You showed the pill detection model, for example, in the demo. Do you have to upload your own data? Did someone take images of all those pills, or were they synthetically generated using some sort of Python script? Or
it's an open source data set.
Okay. So
I think it was basically. Look, I don't actually know the answer, but just looking at it, it looks like it's actual real images, and they've done background replacement or something because it's got a lot of FLAC and hash, kind of visual hash in it.
For sure,
they've made it pretty hard.
Yeah, some sort of image manipulation script for sure. And
okay,
but so you have to upload your own data set.
So, to come back to your question, we provide a bunch of the open source data sets that we've already uploaded. People are always uploading other open source data sets that we've never heard of. And then, like, for the real production quality models, that when people are serious about building something for a product, they typically have to either create their own data in some way or gather their data in some way. Yeah.
Okay.
Cool.
Do you have to bring it in already labeled as well?
Yeah, we have a labeling service that we partner with, and that's within the platform. But most of the time, it's already labeled.
Sure.
Good. What else we got here? Any more goodies?
Sorry, go ahead.
I just saw one question there that I thought would be a good one. Who is the audience for ModelCat? Do you need to have strong knowledge of ML already to use it?
Yeah.
You might have been able to see in the user interface that we really worked hard to make it so that you can kind of think functionally and not have to be an expert on the minutiae of data science and ML to use the thing. And I can say that we've come a hugely long way, and we're continuing to squeeze that. It's actually a very hard thing to do because it pushes a lot of the functionality further down, lower down into the stack. The AI further down has to be more and more responsible, if you like. And so, the last thing any of us want is to be arguing with the thing about what it wants to do or what its ideas are or whatever. That's not its job. Its job is to kind of just do what you ask. And so our aspiration is to make it that a product manager can use it. So that is analogous to what some of the code development tools in traditional software aiming at.
Cool. Yeah, I was looking in the demo you showed, there was a lot of options to show like advanced mode, and then the page got so big, and I was like, whoa, I think that would be a little bit intimidating, but I'm assuming you guys have some sort of way to do, I suppose, is there some sort of like partner programming for a bit? Is there a package, like, or do you just have to jump straight in on your own with your team?
It's, what we suggest is do a test drive if you're interested, or you're asking yourself that question. A user could well be asking themselves that question.
Yeah.
What we suggest is do a test drive. It costs nothing. It takes all of a few hours to actually get a flavor for what you need to do.
Yeah.
It really is that easy. And so, most users, once they've done a test drive, they kind of you have to recalibrate your mental model, because if you're kind of used to Python notebooks or you're maybe a traditional software developer and you're looking at all the libraries which of these libraries do I really need for developing my AI model, this is 100 or 1,000 times less complex. So yes, we have the advanced mode because we need to straddle. Look, the reality is that many of the people listening here are data scientists or ML people in some capacity, and they need control, and they want to have control, and they probably do know, and will be able to contribute beyond what our AI sort of can do. And so we need to enable that as well.
Right. So when you say qualified buyers, is this available to like folks in academia as well, or do you have some sort of program if they're
Yeah. For the test drives are, yes.
Okay. So qualified academicians.
It's just qualified in the sense that it's not a completely automated process. That's an email address, and that's a little form, and
we encourage people to click on that.
Yeah.
This sort of plays along with Katya's question earlier. How long does it take to get from start to finish? How long, would it take for an average user to get from uploading their data, clicking start, and then deploying onto the device?
Yeah. Okay, so it's an excellent question. Many people ask it. Unfortunately, it's a how long is a piece of string question. It can take between. So, Katya, your range of estimates is about right. Hours up to a week is about kind of what I would say. So a week for these large data sets, like, we've got some, people who've been doing automotive, safety related, high resolution images, large data sets, very large transformer models that you're training. And then, that example that I showed, that was probably a few hours, I would guess.
Got it. And do you run this on what's your back end? Are you running this like an AWS, or is it?
It's AWS. We use AWS, and so and Katya, you might be wondering how we do that in a few hours. It spins up a cluster of machines for the particular job. So for you, when you hit that build button or the create button, it spins up a cluster for you. It's not just one machine or anything.
You also mentioned, sorry, Pete. You also mentioned that there was I can't remember what you called it, but a farm of devices that you've already support. Are these like you have a room physically with the devices that it's deploying to check the accuracy and the performance?
Yep.
Very cool.
Yep.
I would be cool a picture of that.
Yes. There is a picture floating around. I think our hardware guy is going to do a beauty shot soon. He said he was going to. Yeah. Yep.
Very cool.
Good.
Oh, Dale has a question, Pete.
Dale has a question. How much does it cost?
Yeah, unfortunately, that's the piece of string again, Dale. But you know, we have a little one pager which kind of gives some kind of guidelines, small, medium, and that sort of production quality,
Right.
which we could share. So if you just ping me afterwards, I'll dig that out and I'll just send that to you. That just again, it gives you a flavor, kind of like what
be cool if there's some sort of tool where you could sort of do a cost estimator on your website.
Yeah. You know, the one of our engineers is promising me the cost estimation model.
Okay.
And you know, it's coming. We've got enough data. So the hard thing with that is the data. It's actually not that hard a model, but it's just yet another roadmap item. So that little meter that said what your probability of success was will also say here's what your cost estimate is.
Got it. Okay. So you do have human engineers. It's not all AI generated. You're not the only employee.
No. You know, that canonical slide of how you do development, that's, you know, for sure a large platform development like this, we look like that.
No. Okay. Awesome. We're coming in the last couple of minutes. I wanted to remind folks, this show will be on our YouTube channel instantly after we finish today. So if you didn't catch the beginning, you can do that. And then also upcoming live streams are here at jffoundation.org live streams. So we have one of these every 2 weeks. You can subscribe to our YouTube channel or whatever your mechanism is. It's on LinkedIn and Twitch as well. But yeah, I think, Evan, this is fantastic. Really appreciate your time. And Jenny, thanks for co-hosting.
Yes.
Thanks everyone in the audience for accommodating our timing things. And any closing words of wisdom, Evan, for the world here?
All I'd say is ping us, and we're very open to partnering. You know, I noticed that there was a bunch of questions about the chips. We're very open to partnering with a variety of different chip vendors, and this proposition works for all of those, including the really innovative stuff that people are doing at the hardware level. So
yeah, and this is like exactly the kind of innovation thing that you almost don't even think of that's happening in this space, like, you know, actually using AI to sort of help with model portability and development and deployment of solutions. So fantastic that you're on the cutting edge of this. And again, kudos on the rebranding Model Cat. Very cool.
Thanks.
For some merch. I have my foundation merch. We need some Model Cat caps or something. I don't know. Cool. All right. Well, thanks everybody. Jenny, thank you again. Evan,
of course.
Thank you very, very much both for hosting, and thanks to the audience for listening today.
Thanks for joining.
Take care.
Okay.